We can also evaluate limits numerically, and in order to do that, basically all we're going to do is use our calculator and calculate what that limit is going to be by looking also at the graph and maybe by tracing some things. Well, the first one I'm going to look at, I'm going to go to my calculator here, y equals, and I'm going to put in my equation there, 2x plus 1, and graph this. And if I trace this at 3, I get that the limit is 7. And actually, if I substitute it in 3 here, 2 times 3 plus 1 is going to equal 7. So my limit there is going to be 7, and that's easy enough. So let's do our second example here. If I go to y equals, I have x cubed minus x squared plus x minus 1 divided, I probably put all this in here correctly, x cubed minus x squared plus x minus 1 divided by x minus 1. And you can actually see before I even graph this, there's going to be a problem here. So once I graph this, I'm trying to find the limit as x goes to 1. And looking on this graph here, it looks like we have something completely continuous, right? But if I trace 1, I get nothing. There's a hole here in this graph. So if I were to draw this, it looks like we're here. If I drew this, there's actually a hole right here. You can kind of see that's a little bit of a hole. So how are we going to trace this? Well, instead of putting in 1, I'm going to go a little bit to the left and a little bit to the right. So I'm going to trace to the right 1.00001. And so if I trace that, 1.0001, and it doesn't matter how many zeros you put in, and I get basically 2. Right? And if I trace again, 0.99999, which would be slightly to the left, I get 1.99999, basically 2. So the limit, as we're approaching from both directions to that point 1, is going to be equal to 2. Let's do a few more examples. So for number 3 here, we have the limit as x approaches negative 5. Again, I'm going to put this in my calculator. So I have x minus 2 divided by x squared plus 3x minus 10. And if I graph this, okay, I'm getting some asymptotes, it looks like. And if I trace at negative 5, I have nothing. It looks like negative 5 is exactly where our asymptote is. So again, I go numerically. Instead of, I'm going to go 1 to the right. So I'll have negative 4.9999999 and negative 5.000001. So negative 4.9999. I get basically 100,000. That's a comma there. And if I do negative 5.0001, I get negative 100,000. So what's my limit? Well, these didn't match up. And because these didn't match up, my limit here does not exist. The limit does not exist. Let's look at number 4. This is actually the exact same function, but we're now trying to find the limit as x goes to 2. So if I trace here at 2, I have nothing. It turns out I actually have a hole at 2. So now we're going to trace again 2.00001 and 1.9999999. So I get 0.1428564. Okay, and 1.99999. I get 1.14285716. So as we keep going, these aren't matching up, but really they are getting very close to one another. So it looks like our limit here is going to be that 0.14285. Good? Okay, 3 more examples. Let's look at number 5 here. The limit x over the square root of, let's take our calculator here. So we have x divided by parentheses, second square root of x plus 1, and then we're outside of the parentheses. Make sure you've got that in there correctly. Minus 1. And we can graph this. We've got a little bit of like about a half of a parabola there, it kind of looks like. And if we trace it 0, we have nothing. So we must go negative 0.00001. We get 1.9999. And we'll go 0.00001. And we get about 2. So it looks to me like our limit here is 2. Okay, let's look at number 6. Now number 6, we've got a piecewise function. So we want to be able to enter that in our calculator. And actually there's a way to do this in your calculator without even having to write this in 2 lines. So we're going to write y equals parentheses 0.5x plus 3, close parentheses, open parentheses. Can you see that okay? X is second math less than, so that's number 5, 4, close parentheses, plus open parentheses, and then I'm going to put in my second line there. So x minus 3, close parentheses, open parentheses, x second math greater than 4. So at 3, 4. And we can graph this. And we have 2 lines that really are broken up here. And if we trace 4, it says that we have 0. But that's not actually correct. And we know that because when we're looking at this piecewise function, we can see 4 is never equal to anything, right? It's never actually equal. So what is this going to be? Well, we're going to trace. If we trace 3.9999, we get 4.995. And if we trace 4.0001, we get 1.0001. Well, those are not equal to one another. Therefore, our limit here does not exist. And we can actually see on this one, graphically, if we're approaching 4, we know that it's not approaching to the exact same point. So these are not going, there's not going to be a limit here. All right, let's do number 7, our last example. Very, very similar. Looks like all we have to do is change our last equation here. So I'm just going to go in and do that rather than retype everything. So I'm going to have 9 minus x. And I graph this. Now I've got what looks like sort of an absolute value function. And I want to trace this at 4. And I have 0 again. Again, we know that that cannot be the limit. That cannot actually be accurate because we don't have an equal sign underneath our less than and greater than symbols here. So what's our limit going to be? We again trace 3.99999. We get about 4.99, about 5, and 4.0001. 4.9, it looks like to me we're going to be very, very close to 5. So our limit is 5. All right, that's about it for evaluating limits numerically. Now, on our next video, we will evaluate them algebraically.